And so yeah, so today's recitation, we're gonna really try to use our time to cover a little bit about what you're supposed to do, what you're supposed to know after you did the linear regression, after you do the ordinary least square. So we're talking about a couple of theorems. Let's just go ahead, jump right in. The first theorem. Okay, so the first theorem is really about when you have a linear regression already done. Like you have the data, you fit a linear regression model, everything is done. The first theorem is really about testing the hypothesis of essentially a linear combination. So here we say hypothesis testing. And this is for linear combination. So what do I mean by that? Specifically, we're talking about beta 0 plus beta 1 x. X. All right. So the text we use a weird notation C, and this is because we're treating that as a constant versus in linear regression, they're X and Y. So that's okay. We're gonna stay with the textbook notation. Just letting you guys know that's a relationship. So we're gonna say let C0, C1, and C star be some number, some arbitrary number. And then, of course, we are assuming that their C0, C1 are not zero. And suppose we have a hypothesis, null hypothesis, H is 0. That's going to be C0, beta 0 plus C1, beta 1 equals to C star. Versus alternative hypothesis, H1, that's going to be left-hand side is exactly the same. So let me just copy this down. And it says not equal to C star. And let me just copy down the whole thing first. So at significance level alpha, we say that you can compute the test statistics. And this notation is U01. And let me just copy this whole thing down and I'll explain it. It's quite long, so bear with me. This is C0 over N squared plus C star minus C1 parenthesis square over SX square. And then the whole thing, you take this and then times C0 beta 0 hat plus C1 beta 1 hat minus C star divided by this thing. There's a superscript T here, just to illustrate what it means. So this is the statistics, the test statistics of this theorem, and the conclusion of this theorem says you can then essentially compare U01 with critical value, and this is a T degree of freedom is n-2, and this is inverse, and then inside of this is your alpha, so 1 minus alpha over 2 because it's two-sided. Okay, so this is a lot of information, and we are really trying to just understand what's going on here. Now, before we move further, let me just walk through this a little bit. So exactly what this theorem says is the following: in the beginning, you're going to have some sort of fit, right? You have data X and Y, you fit the model. So what do I mean by that? Is this? Suppose that's your y-axis, that's your x-axis. Maybe you can think of this as x, this is as y, and then your data just a bunch of dots, right? Something like this. And then you fit a line just like that, right? So this is like your line of fit. So we're gonna call that fit. And these are the data, right? So that's what's happening. That's a situation, that's a setup, done. Now, once this is done, right, the problem says, okay, the problem says, I'm going to give you some arbitrary number, right, some arbitrary number here. So what I mean by that is, you can kind of imagine like, what if I give you like, let's say there's a dot here, right? There's a dot here. And then you observe some sort of x. In this case, it's C1. So, but it's okay. We're just gonna call some magical x, right? Let's say x naught. And then using this x naught, right? Using this x naught, you're able to make a prediction using the fit, right? So where is that? That's exactly going to be on the line. So that's going to be your real value, the real y, and that's going to be your prediction. Okay, so how good is this, right? What are we talking about? Is it good? Is it bad? How do we know that? Well, you can think of the following way. So like imagine there's a magical line here, and that's the following. So if your red dot and your green dot, let's say suppose it's far away, right? So what that means is this red dot come from a distribution like that, and this green dot come from distribution like that. So then if that's the case, you can kind of take a leap of faith that the understanding here is there's no overlap or very little overlap. I'm just going to go ahead and say no overlap, just to make the case more dramatic so that you guys can see the extreme point and extreme situation, what's going on. And if that's the case, you can kind of say, okay, this red dot and this green dot probably come from different distribution, right? They're different. So we're going to say different distribution. Alternatively, right? Alternatively, they're close to each other, right? So what do we mean by that? Close to each other means this. There's a dot here, that's red. There's a dot here, that's green. The red has a distribution just like that. The green also has a distribution just like that. Sorry, let me draw this a little bit better. Because we want to show overlap, so you're not supposed to tell which was which. Something like this. So what's happening here is there's going to be lots of overlap down here, right? You're not supposed, like, you can't say with confidence that these two dots come from different distribution, right? You can't say that. At least you can't say that with confidence. So then what's happening is here you say, okay, there's a lot of overlap. And then you can say, okay, they're same distribution. Does that kind of make sense? So in other words, in the classical statistics sense, right? Like we're not talking about machine learning or AI or we're looking at accuracy, that sort of thing. Like we're backwards in time and we're in classical statistics sense. We have a fit, we have a data. Now I give you a new data, this green dot. Either it's accurate or it's not accurate. But how do we know that, right? We know that from hypothesis testing, which is what you say that's the same from the predicted. You say that the green dot has the same distribution from the the red dot, the predicted value, or they're different, right? So if you can say that they're same, if you're confident say that they're same distribution, then it's probably a good fit. That's sort of the reasoning behind. Instead of in machine learning sense, we're looking at R square, we're looking at accuracy, that sort of thing. So that's the intuition going behind this hypothesis. Okay, so now with that being said, we can jump right in and just take a look at the question. In this type of problem in the final exam, I'm pretty sure it's going to be a similar problem in the final exam. Before you guys had MLE, Bayes, methods of moment, sufficient statistics, consistent statistic, that sort of thing. MLE, and then maybe there's a weird function, and then you solve with like invariance property, that sort of thing. So all those things gonna be, I'm pretty sure that they're all gonna be tested again in the final. And then in addition, you guys are also gonna see a problem with linear regression, right? And so this is one of the problems. So bear with me, and let's continue from here. Let's look at one of the examples. So this will be example 11.3.3. The problem itself is relatively easy. It's really just they give you a number and you plug in the number using the equation. But I want to dive a little bit deeper into what goes behind it. So usually the problem will give you usually give you all numbers. So let's say this is H naught, that's your null hypothesis, that's your beta 0 plus 201.5 beta 1 equals to C star is 24.5. That's alternative hypothesis, that's beta 0, 201.5, beta 1 is not equal to 24.5. So 1 equal, 1 not equal. And then let's write out the numbers. Let's see. So C0, that's 1. Like imagine there's a magical 1 here, right? That's a C0. And C1 is here, so that's this number. So C1 is 201.5. You also need to know the variance of X, SSX, 530, X bar, that is going to be 202, and then sigma T, that is going to be 0.2328. And then on top of that, you have beta 0 hat to be, I'll just round up to the whole number. So minus 81, beta 1 hat, that is going to be 0.52. Let me double check my number. Yeah, so all those things are given to you. And essentially, it really just comes down to, the plugging the number and you just do it, right? I think there's a student that just joined late. So right now we're talking about example 11.3.3. And in the beginning, what we just talked about is the intuition behind this theorem hypothesis testing with the linear combination. So don't worry about it if you're not following up. This entire thing is recorded and I'll post online. So you can always check the video afterwards. Okay, so let's continue. Here, once you have all these numbers, you plug in and you just do it, right? So the equation we're gonna use is this guy, right? So literally, I can just take this and copy it. So I'm gonna crop that, and I'm gonna copy, and I'm gonna paste it down here. All right. So let's plug in a number, right? So what do we have? We have, oh, I forgot to tell you guys, n is 17. So that's 1 over 17 plus, that's 202 minus, I'm sorry, I made a mistake. That's not 202. This is, X bar is 202. What did I write? 202. Okay, yeah. Minus C1 is 201.5. Don't forget a square over SS square, that's 530. And then that is going to be inverse square root. And then inside here you have essentially minus 81 plus 201.5. That's C1 here. And then minus C star, which is going to be 24. Sorry, let me, I need a beta 1 hat. Beta 1 hat is 0.52 and then minus 24.5. And then this 24.5 is here. And a sigma, that is going to be, let's see, that's going to be 0.2328. So it's quite long, lots of small numbers. So let's stick with that. And the final results, once you work out the math, it's going to be around, about negative 0.22. So that's the math. You plug in, you work out, and that's the final answer. So what's happening from here then? So we work out this number. How do we compare? So what we do is we compare with t distribution. So the story here is this under null hypothesis. Okay, null hypothesis. What is null hypothesis? Null hypothesis is this one. So if this one is correct, okay, if this one is correct, then this statistic should be able to asymptotically converge to t distribution with degree of freedom n-2. All right. So let's discuss. So discuss if, so I'll just say under null. So under null hypothesis, H0, what's happening is your U01 will converge to T, and the degree of freedom is n-2 at alpha level. Like if it's alpha level, if it's the alpha significance level, then it's 1 minus alpha over 2. Okay, so under null, that will be the case, right? But then how do we know that is not the case? Well, you compare this with the critical value coming from the t distribution. Okay, so the way we write that is the following. So the critical value, so check. Usually you check from table. So I'll just write check table from here, and then the critical value is going to be, we use t inverse, and that's because this is the CDF of t distribution, right? And just bear with me, I'm gonna write this down, and then I'll tell you guys what's the interpretation. So usually the n-2 goes down here, and then we write 1 minus alpha over 2, just like that. So so yeah, so that's gonna be how you find the critical value. So let's talk a little bit here. I think last time there somebody asked me questions. So the way to understand is the following. So let's say you have some sort of I'll just use normal distribution as an example. So let's say that's a bell-shaped curve, just like that, right? And then I'm gonna take a further step and say that's 0, 1. So you can kind of think of this as a standard normal. Okay. This is the PDF, right? So someone write like that, it's a PDF. So let's write a note. This is going to be your PDF. And then what is going to be your CDF then, right? So the CDF is going to be something like this. So this is your CDF. So recall in say a z-test, right? The very basic hypothesis test in the z-test. The z-test in the end, what is the critical value? We're using the phi inverse, right? So this CDF is actually just phi. And then you have some sort of number in here, right? So that number corresponds to this number. So give me a number, the phi will tell you the probability of the observation that is below that number, right? So what do I mean by that? So let's say you have a dot here. I'll use a different color. Let's say you have a dot here. I give you this dot, right? You call it whatever, like if you call it, let's say call it z. Then what's happening is it's gonna be here. Then this dot, so phi of z, that is the probability under z, but under the standard normal distribution function CDF. So it's the same story here, right? So how do you recover this z? You use inverse. Does that kind of make sense? And you say, let's say this is let's use a standard number. So let's say the standard number, what is this? This is let's say this is 1.96. This is negative 1.96, and that should be around like 95%, something like that, right? You should double check that because I think it's like not 95 point something, but let's say just pretend that's 95%. You can kind of think of it like this, right? So how do I know this is z? Well, you use inverse, you throw 95% back in there, right? So that's how you get, and that's how you obtain z, right? So that's your critical value. So it's the same idea here. Okay, so you have a t, and then you throw the probability or you throw the significance level in there, and then you recover the critical value, and that critical value is going to be what you compare with your statistics. All right. So here we say, so if you compare this guy with your statistics, and you can say that you reject the null. So the answer is going to be reject null if your statistics is greater than critical value. All right. So that is how you solve this kind of problem. I can tell you guys that usually this problem is not going to be existing like by itself in an exam. Usually it will be like a two-parters or three-parters, right? So if it's two parts, this will probably going to be like the second part, something like that. Because sometimes it could be the third parts, but I think most likely it will probably be the second parts. Because the first part is really just about how you find these guys, right? So so let's see what's happening from here. So the next line of business, once you're able to come up with a hypothesis testing, right, you should be able to write out the confidence interval. Okay, so sometimes people they in the beginning of your learning curve, people tend to separate them. I think that's probably that's not strictly wrong, but I think you are probably better off to associate them together because they're kind of like the same concept. If it falls out of the confidence interval, you can kind of say reject the null hypothesis, that sort of thing. So let's just continue to finish the entire thing, and I'll tell you guys, the big picture after that. So with this part being done, you have the test statistics, and you know how to reject or how to accept the null hypothesis. And after that, the question might ask you about confidence interval. So this is actually a theorem. So you can just directly write that. So here, I'm just gonna save some time and say, based on the above situation, we can write out the confidence interval. And it's going to be this thing. That's 0, 1, beta 1 half, plus minus sigma, and that's for t, C0 over n, plus C0 x bar, minus C1 square over S of x squared, minus 1/2. And this is Tn minus 2 inverse 1 minus alpha over 2. All right. Okay. So right. So actually, I'm sorry, I made a mistake here. This is not inverse, this is square. Okay, and then you can kind of think of this as critical value. Okay, so I'm not going to redo the math again. It's really just the same number from up here, and then all you gotta do is plug in these numbers, and work out the math, and you're gonna get a range. All right. So so this is the kind of so now, with that being said, I'm gonna give you guys a big picture, right? So what's happening is the following. Let's draw a line. All right, so what we have done here is two parts. This is one part, you can call that A. And then this is another part, you can call that B. But usually before the exam ask you this kind of question, they're probably gonna ask you to figure this out first, sorry, figure this out first. Does that kind of make sense? So now, if you put all those things together, like remember last presentation, we talked about how do you find beta 0 and how do you find beta beta 1, right? So if you put everything together from what you have learned in linear regression and plus a little bit hypothesis testing, really the entire question will probably look something like this. So first of all, you probably give you some data, right? So the question is going to be just like the following. So provide you with the data, and then maybe you have like X, give you a bunch of numbers, Y, give you a bunch of numbers, just like that. And then the first question is going to be using the linear use least square to find the coefficients. Find coefficients of y equals to beta 0 plus beta 1 x, right? And there's nothing magical here, right? You're just solving least square. So what you do is you work out the least square formula first. So least square formula, I'll just write it out because it's exact same derivation from what we did last time. So I'll just write out here, you know, use this Q, and then what you have is summation, subscript I, yi minus coefficient minus this xi square, right? So it's kind of like a loss function sort of thing. You know, that's how many mistakes that you're making, right? The discrepancy between your model, your prediction, and the reality, like the truth of yi. So once that's done, you take partial derivative. And how do you do that is you take this, so partial beta 0, q, you set that to 0, you solve it, and then you do the same thing, beta 1, right? And that gives you another equation. So this is what, 2 equation, 2 unknown, right? So you're able to solve for beta 0 and beta 1. So immediately you solve for beta 0 is this, beta 1, and then beta 1 is going to be something like this. I'll just use a shorthand notation, SXY as over SSS. And if you want to know what they are, they're in the previous recitation. So you know, once you have the results, you can essentially just it depends on what the question is asking. Sometimes the question are asking you to do this entire thing, which I highly doubt it. Most likely question can just, they're probably going to give you something like this. They're probably going to give you a number that's small enough so that you can just directly compute, y bar, x bar, and then you just go do it. And then, you plug this thing in, you solve for these two things, right? So that's going to give you essentially a setup of the situation, right? So you have a data, you fit a linear regression model, done. That's the situation. So once you have your model, right? Once you have a model, then you move on to B. B is exactly the first theorem that we talked about today, right? So B will give you a point. Let's say suppose you observe a point. So what's the point? So we're going to call it C1, C star. And let me just move this to the next page. So B, suppose you observe this, and then you do hypothesis testing, right? So how good is this point? Well, how do we know that? Hypothesis testing. So H naught C0 beta 0 plus C1 beta 1 equals to C star. Versus alternative hypothesis is the left-hand side is exactly the same, but it's not equal to C star, right? So recall that graph that we just draw, right? You have your X, you have your Y, you have your bunch of data just like that. You fit a linear regression, right? Now I give you a point, arbitrary point somewhere here. And then it has a X coordinate, right? It has a Y coordinate, right? And then you look at you look at the model, right? This is what you just done, right? You have the model. So once you have the model, you're able to make a prediction there. So how good is there, right? How good is this red dot? Well, you can think, you can think something like this. And then really, we're just drawing distributions. Make sense? So hypothesis testing tells us, are they the same distribution or not? Okay, so if they're relatively same, you can say that with confidence, then maybe it's a good model, right? If you're like, hey, wait a second, we're rejecting the null hypothesis, they're not the same, absolutely not, right? With confidence, they're not the same. Then it's probably a bad model. So that's kind of the reasoning going behind. Okay, this is before machine learning, right? This is in conventional statistical sense. All right, so how do you do that? Well, you use your formula, right? So you compute u, and then you check with a critical value. So t inverse n minus 1, 1 minus alpha over 2. All right, and then once that's done, you can say reject null if u01 is greater than this critical value. All right, so that's going to be your part B. All right, so after that, you're likely going to also see a part C. Part C is just about confidence interval. Okay, so I think up to this point, it's probably more like a memorization game, to be perfectly honest. It probably takes a little bit of work to memorize this. Especially they don't allow cheat sheet. Oh, sorry, that's not minus, that's plus, that's plus minus. And then here we have a sigma t. Let me just copy this one more time, and I'll tell you guys how I memorize it. C0 x bar C1, that's a square over what else? S is x square, and then parenthesis minus inverse, half inverse, and t n minus 2 inverse 1 minus alpha over 2. Is that right? Let me double check. Yeah. All right. So with that being said, all of this really comes down to asymptotic statistics. Okay. So all that is essentially consistent with everything we've done before, right? So you let's say you have MLE, you're able to work out the asymptotic statistics, right? Or asymptotic distribution. In the midterm, there are problems that you have to use delta method to find the asymptotic distribution. All that stuff is related, right? So what do I mean by that? Really, the idea of this entire framework goes all the way behind how we understand the variance of essentially a linear model, right? So what do I mean by that is the following. Here, give you guys a little bit of intuition. So before I get to the math part, let me set up a situation. So the situation is the following. So how do you memorize it? If you have a linear model, right? Let's suppose you have a linear model. And usually people write something like this, right? That's a linear model. In this framework that we've just done, comparing linear model, hypothesis testing, in this framework, we're using C. Specifically, we're comparing this. So C0 beta 0 plus C1 beta 1 hat plus C star. We're really looking at this plus this, and we set that as T, right? So set this as T. So that might look a little bit unintuitive because upstream we talked about something like this, right? So if you move this guy to left-hand side, that should be like a minus C star, right? Something like that. So really, intuitively, you can kind of think of it as the difference between these two equations, right? The difference is called T, and you're looking at the variance of that difference. But since but since these guys are just arbitrary numbers, then you can, just write plus. That doesn't really change anything. I mean, the worst case scenario, you change the sign of this, right? You just add minus here. Does that kind of make sense? So that's really the difference between your linear model and the true value of that observation, right? So really, we're talking about this distance. That's going to be your t. All right. So with that being said, now we can look at the variance of t. So what would be the variance of t? So variance of t is going to be, and I'll use the formula. This is going to be C0 squared variance beta 0 hat plus C1 hat variance beta 1 hat plus 2 times C0 1 covariance beta 0 hat beta 1 hat. All right. So I don't know if you guys like finance. If you guys like finance, you can kind of recall the capital asset pricing model. The risk of the capital asset pricing model is exactly same as this formula, and that's for two assets. So kind of corresponds to beta 0 and beta 1. That's kind of how I memorize it, by using a real world situation. But that's like, finance classes complete outside the scope of this course. So the question is the following: once we arrive at this formula, what are we supposed to do, right? In the beginning, what do we say? We said that if you fit the OLS, right? If you fit the least square, you're gonna get something like this, right? You fit the least square, you solve it. It's a 2 equation, 2 unknown. You set to 0, right? And then the result is this guy and this guy. Okay, so you can actually you can actually find the asymptotic distribution of your beta 0 hat and beta 1 hat, right? Using everything that we've learned before. You can find an expectation, and you can find a variance, and then you can find an asymptotic distribution. Okay, so this is actually come from beta 0 hat, right? So you can kind of take a guess that it's beta 0, right? So what I mean, so in other words, beta 0 hat is unbiased, right? So the one important theorem, or you can say characteristic of linear regression model, is what? The linear coefficients are unbiased, right? So that's something interesting. And what else? Variance. So if you derive it out, the variance actually looks something like this. And there's x bar here over sx squared. Okay. So that's the asymptotic distribution for beta 0 hat. Okay. Now, you can kind of think of this as expectation of beta 0 hat. You derive it, it will become this. And same thing here, variance of beta 0 hat. You derive it, it will become that. All right. So that's for beta 0. Now, what's happening with beta 1 hat, right? The variance, what's happening with variance of that? So variance of that, let me write it here. This is actually come from the following. So I'll write, I'm running out of space here, so I'm just going to write like this. So that's beta 1 hat. This is also come from the asymptotic distribution, right, of beta 1 hat. So what is that? So that is beta 1. That's the same because it's unbiased. And here we have summation xi minus x bar variance of yi over sx4. And if you look closely, right, this is actually this actually can be, oh, I'm sorry, I forgot a square here. This can actually be simplified a little bit, right? So here you really just have sx squared, and then the bottom sx4 you copy down here, and then the variance of yi, usually people replace that with sigma squared, right? So you can kind of just, do this, erase that, and then write sigma square. So now what you notice is this and this cancel out, and what you're gonna have left is sigma square over sx square. Make sense? So now, the last piece is this guy here, the covariance term, right? So the covariance term is going to be, I'll just write it down here, it's rather simple, x bar sigma square over sx square, all right? So this it's just an individual term, but these two guys come from their asymptotic distribution. Okay, so if I were you, I'll probably take some time and try to derive these three things, and see if you can understand it. So derivation is really just you set it up. It's just a lot of numerical steps, right? You set it up. So this is how you do something like this. Expectation of beta 1 hat. You try to solve it. Variance VAR of beta 1 hat, and then you try to solve it. So the setup is a rather straightforward, right? You have your coefficient. Beta 1 hat is whatever we found, right? Like from least square, we found this guy. Beta 0 is this guy. You take expectation of both of them, right? Or you take a variance of both of them, and you can solve for the asymptotic distribution. Worst case scenario, you don't know how to solve it, you can just probably Google it, and I'm pretty sure there are lots of materials online deriving this kind of. This is a pretty standard stuff. So my guess is in the exam, they're probably not going to have to derive this because it's just too long for just for the span of the exam. This is probably too long to put in the exam like this. To derive this whole thing. That'll take way too much time. But you should definitely know where it's coming, like where this formula is coming. Like you should definitely know where this comes from. You should definitely know where the statistics is coming from, which I wrote up here, right? You should definitely know where all these things are coming from. Well, they're coming from the asymptotic distribution of beta 0 hat and beta 1 hat. All right. So now with that intuition behind, you can kind of take a second look of this equation, right? Take a second look at this equation. And then what we're going to notice is the following. This term here is kind of like some sort of difference, right? Like, you have your model, your minus C star. So some sort of difference. So you kind of call that T, right? And then here we have this inverse, 1/2. This is 1/2. 1/2 is really just about square root, right? The inverse is just 1 inverse, right? So I can, essentially get rid of this power term and write like that, right? So that kind of looks like what? So if I do that, I'll take a leap of faith, and then that'll kind of look like something like this. It's a difference over square root of what? Some sort of variance, right? Everyone follows, right? So difference is referring to this difference. Variance is the kind of thing like, I get rid of a 1/2, that's a square root. I get rid of a minus, so that's 1 inverse, right? So in other words, I'm really just moving this down here, right? So it's kind of like some sort of, square root variance term going on down there, right? So now you kind of have like a more intuitive understanding of what's going on, right? Difference, you just take the difference, right? It's given in the problem, right? You take the difference. So this piece should be easy. This piece down there is coming from the asymptotic variance, right? So if you spend like some time to check out that derivation, you should be able to memorize, this stuff here, right? And you put those things together, that's your test statistics. So in other words, it still follow the conventional sense of what we've been seeing in, say, for example, z-test or t-test, right? Here we're testing the linear model. It's exact same. Philosophy that we're doing here, right? So, okay. So with that being said, I think that's pretty much everything I want to cover. hopefully this is clear. I think this picture says a lot of information. I use a picture or graphical aids, or people is what people call it, graphical aids, to help me to just help myself understand it. So hopefully that's helpful for you. I would encourage that you go through this entire pipeline, at least 2-3 times before study for the final, right? So imagine yourself this big picture, right? You have your data X and Y. You fit the model first. That's part A. Right? Hopefully that's easy. Just a lot of math, a little bit tedious, but hopefully you can get that done. So once A is done, you ask yourself, I have an observation right now. What do I do from there? Is it good? Is it bad? What do we do? Well, the answer is hypothesis testing. Then the question is, okay, if we're dealing with hypothesis testing, what is the test statistic, and what is the critical value, right? Test statistic is really just about plugging formula, and the formula comes from something like an estimate over square root of some sort of variance, okay? And then the critical value comes from usually some sort of distribution, T or some other test is F, or anything like that, inverse to recover the critical value. And then you compare the critical value with your test statistics. Okay. I'm just gonna go ahead and take a leap here and say that sometimes the question will ask you. So let me put a remark. So here, this is a remark. Sometimes instead of asking you, okay, this is a test statistics, this is the critical value, give me the answer. Right? Instead of going from that direction, sometimes the test, the question will ask you like the p-value, right? Or like the power of the test, right? So like something like p-value, or like power of the test, that's essentially referring to the same thing, right? It just, left hand side you do T inverse to recover the critical value, but right hand side you just look at the T, right? And you compare the p-value from the table. Okay, so they can both be referred from the table. So the way I would memorize all of this is essentially by using a standard normal distribution, because that actually looks very much like the T distribution. So you can kind of take a quick pause and just draw ourselves a standard normal distribution, something like that. And then you can say, usually the go-to example is that's a 1.96, that's a minus 1.96. And then, if it's two-tail, it looks like that. And then if you want to look at the CDF, you draw a CDF, all right? And then, draw something like this, and then you look at that, and I'll probably give you like whatever, like 95% or something like that. All right, so it's technically speaking is two graphs. I'm just cheating a little bit and put them together. Yeah. So don't worry about the table. Pretty sure the exam is going to provide you a table. But if you feel like that's not the case, or something that you can't find it, I think you can always ask the TA during the exam. It's okay. It's not cheating. I mean, I think it's a fair question to ask. So yeah, don't worry about the table. I think some people ask me, are we gonna prepare a table? Yeah, the table is provided just like midterm. If you feel like you need something that's not on the table, then that probably means that you don't need that thing. So it's kind of like a quick sanity check to know whether you need a table. Yeah. So that's B, and then C is just write out the confidence interval. Usually it's just you plug in the number and you just do it. Okay. So let's see. We're almost at a time, a few minutes before, so that's good. I think I pretty much covered everything I want to cover. Final words. Exam, of course, right, is coming up December 1st, December 2nd. I don't know which sessions you guys are. I'm gonna be proctoring December 2nd, so which is the second session. and hopefully best of luck. And you can always email us for questions. I think there's another office hour coming up. I think either today. I think later today there's office hour. So good luck studying. I think you guys are almost there. After the lecture, I think that's pretty much all the materials. A couple of chapters about all the inference part, right? The MLE, base, methods, moment, invariance property, that sort of thing. Find asymptotic distribution, and then the only new material after midterm is linear regression, and the least square is a little bit new information. Hypothesis testing is perhaps a new information. But after that, I think the asymptotic stuff is consistent with what we've been seeing in midterm. So hopefully that's not going to be a problem. All right, I think we're good to go. I can stay over for a few more minutes to take some questions. If not, you're good to go, and I'll see you in the exam.
Thank you. I have a question. Yeah, the difficulty of the finals, is it going to be the same as the practice sample, or is it going to be harder because the midterm is, pretty easy? So is the final going to be much harder than the practice exam? Exam.
I don't think it's going to be much harder. I think it's probably going to be on par with the practice. So if you can finish the practice, let's say you cover up the book and you do it honestly, don't cheat. And you work out the practice, and if you can successfully get 90 or 95, I think you don't have to worry about that. There's no reason you have to worry about the final.
Okay, thank you. Can I ask a question from the homework, or should I wait until the office hour?
Maybe wait a little bit and let other people ask questions first, and then maybe after that you can stay a little bit longer, or you can ask in the office hour. It's but I want to give other people a chance to ask questions first. Yeah. If there's no other questions, then you can just go ahead and
thank you. But I didn't